have point charge located at P, then potential in the fields at this point P. So the charge is here at this distance R minus RP. Then the scalar potential is called Richard potentials. Top one. And the vector potential is here is top part is 1 minus n dot beta, and n vector is this, it's directed from the charge to the field point, and beta is normalized velocity. And the fields like this. B is equal to that plus A. And so far we have studied two special cases, right? And we first of all we solved the problem in general. We found the electric and magnetic field, and the radiation part of the electric field was this. I'm just recalling what we already have, where this R is a shorthand for this quotient, and B, as we saw, cross E. We also had this special case of linear acceleration, where this term was 0, and we found out the radiation pattern, which was this. The D prime frame beta dot square sine squared theta 1 minus beta cos theta 5. And just to remind you, when we had dp of t, there was this power of 6, which is just an additional 1 over 1 minus beta cosine theta factor. अगर आप इधर जाकर अपने उन नोट्स को रिवाइज करें जहाँ पे हमने डॉपलर शिफ्ट देखी थी, तो you will realize कि when we had, let's say, ये सिचुएशन हमने क्लास में देखी, there is this radiator of light and then there is a receiver here. So if this one radiates at an angle theta prime in its own frame, this sees radiation at an angle theta in its frame. If this is moving, then I think the cosine theta was something like this, or maybe it was the other way around. This expression. The theta is seen by here and theta prime is. Well, if you have theta and theta prime, it becomes plus. So this essentially is the Doppler shift factor. So it's already incorporated. So this was for the linear acceleration, and the total power was just an integral of this distribution over the solid angle. We found it to be this is when beta is small. And for a general case, this is where gamma is 1 over 1 minus. और अगर हम इस पैटर्न को देखें, ये जो फंक्शन, so this is sine square theta और 1 minus beta cosine theta. तो इसको हमने देखा था, it's something like this. So let's say this is the direction of the velocity of the charged particle. Okay, so this is the particle going this way, and theta is being measured between the observation point and the axis of the motion. So इसको अगर हम देखें, so theta 0 gets 0, क्योंकि ये 0 होता है. So no radiation here and no radiation here, and it is maximum at theta is equal to 90, because then this is 1 and this is also 1, क्योंकि ये 0 होता है. So in between, when theta goes from 90 to 0 or 90 to 180, this number stops decreasing and this number start to decrease as well, right? So because this number begins to increase from 1 to 0, because theta 90 पे ही हो जाएगा 0. So it's 1 minus 0 is 1, and then when theta increases, this will become less than 1. Or so it has an effect of increasing, but since this is decreasing, so overall effect is a combination of the two. And roughly the plot comes out like this, which means this is a polar plot, so it's 0 here, so maximum here, and then it's decreasing as we are going on. So the particle is radiating. No, this was the situation when beta was small. So if this beta is small, this is roughly close to 0. So we can always take this to be 1. So this is just sine square theta, this is this value. Right? And when beta is large, so you can see, let's say beta is 0.5. So then when theta is so this thing approaches to 0 at this thing. So since this is always less than 1, so this number is greater than 1. You have a minus 1 more. So this is beta is 0, so ये कभी भी हो सकता है. This number is less than 1, so this is never 0. But this is the smallest when cosine theta is 1, right? And cosine theta is 1, but this is also decreasing. ये हमने किया था इसको arbitrary beta. Yes, we actually found its d by d theta and found its maxima, and it came out to be at so maxima is cosine theta 1 plus, actually we use a different algebraic method. So he has found maxima in the observer frame. ये जो बुक नोट्स के अंदर जो फार्मूला है वो ऑब्जर्वर फ्रेम उसने पहले यहाँ पे फिक्स कर लिया एंड फाउंड dp of t by d ओमेगा और उसको उसने मैक्सिमाइज किया. हमने जो यहाँ पे किया था हमने पार्टिकल के फ्रेम में इसको मैक्सिमाइज किया. सो यहाँ पे 5 था, आई थिंक वो समथिंग 1 plus 15 था और यहाँ पे 3 बीटा. ठीक है, इन पार्टिकल फ्रेम इट वाज 1 plus 15 बीटा स्क्वायर over 3 बीटा. And in the observer frame, this is 1 plus 44 beta to up 6 के साथ maximize. But anyway, the important thing is this, that the radiation pattern is something like this. So इसको आप 360 degree से you revolve करें. So it is something of a balloon which is elongated in this way, but it's coming to 0 in axial direction exactly. Okay, theta 90 is 0 equal. At theta 0, since this factor is 0, this is not 0, so it's going to be 0. But as beta increases, this becomes very short. So it's a beam like this. So this is what we had for the linear acceleration case. And we also saw that the radiated power, the total radiated power, is only a fraction of the force that accelerates the particle. So we can run the accelerator very easily. For the second case that we were talking last time, that acceleration perpendicular to velocity, then a situation like this, आपने बल्कि specific case लिया था. Let's say this is z-axis, this is x-axis. We imagine our particle to be in xz plane, and at a particular instant we consider the particle to be at the origin. It was going up just at the origin, going up, and it was feeling a force along x-axis, and it had its beta along z-axis. So just this move. थोड़ा आगे जाके बीटा न्यू हो जाएगा और जो बीटा डॉट है it's like this to some origin. So you imagine this is z, this is x-axis. So particle is going like this. So in this case it actually doesn't have to be circle because we just considered one instant. This one circle is only a special case of this. So this is acceleration perpendicular to velocity. तो अब आपका क्या होता है? You have an accelerator. आप पार्टिकल को चार्ज करते हैं, पार्टिकल असल में आ रहे हैं. They are linearly accelerated. और यहाँ पे आपने मैग्नेट लगाए हुए, they just bend the particle only at this point. So जहाँ पे वो bend होंगे, the situation is like this. क्योंकि वो magnetic field आपको apply करें, the charges will feel a force perpendicularly this way, and they will turn from the straight path along this curve. So just at that moment, this thing will apply. अगर circular motion है, you have a constant magnetic field upward everywhere, so the charges are going in circular motion. So that's just a special case where you have an acceleration perpendicular to velocity at each point of the motion. लेकिन this point पे भी है, this is going to be valid. So हमने last time ये work किया था. This particular case, dP by d omega t square beta dot square 4 pi c So this was the angular distribution of power for this special case. And we are trying to see the radiation pattern. Okay. So when we have a non-relativistic case, that is beta is small, it's roughly 0, then the radiation pattern is whatever this is, we call it the C1. Beta 0 kar de, so you have 1 minus sine square theta cos sine square phi. This gamma would be roughly 1. So we have this as a pattern. And for a general case, the pattern is like this. And let me also work out what we usually call ultra-relativistic case. So in general, that's the pattern. For small beta, this is the pattern. For large beta, when beta is roughly 1, which means that gamma is very, very large. So in this case, we can try to approximate this thing as follows. So 1 minus beta cosine theta, I can write it like this. Right? So this is still 1 minus beta cosine theta. नीचे 1 plus beta को से मल्टीप्लाई कर दिया, ऊपर भी कर दिया. But now I can write this cosine square as 1 minus sine square. तो ये बन जाएगा 1 minus beta square minus plus beta square sine square theta. And और ये जो है जो कि beta roughly 1 है, और इस केस में होता ये है कि अभी हम देखेंगे थोड़ी देर में. You can write down this, take me at my words कि रेडिएशन जो है वो सिर्फ स्मॉल थीटा पे ही होती है, और उस वक्त में दिस थीटा इज वेरी स्मॉल, सो आई कैन अप्रॉक्सीमेट दिस कोसाइन थीटा एज 1, सो दिस इज रफली 1 plus 1, so this becomes 2. So we put an approximation. And at the same time, I can approximate this sine square theta is just theta square, and this 1 minus beta square is nothing but 1 over gamma square, so plus beta square theta square over 2. So ये gamma नीचे ले जाते हैं, so this is 1 plus beta square theta square gamma square over 2 gamma square. So this is what we can approximate 1 minus beta cosine theta with for large gamma. So इस पे basically दो approximation है, एक तो gamma large है, which means beta is roughly 1 plus theta is small. So then ये बन जाएगी चीज C1, यहाँ पे आ जाएगा ये फैक्टर, तो ये बन गया 8 gamma 6 Q1 minus 4 gamma square sine square theta cosine square 5 1 plus beta square theta square gamma square. So ये अल्ट्रा रेलेटिविस्टिक केस में ये बन जाएगा, provided that theta is small. Let me now show you this thing on mathematical, and you'll be able to see the profile. But before we do that, while the computer is running on, इस फैक्टर को अगर इसको दोबारा देखें तो पहले तो एंगल अपने ध्यान रखें थीटा और फाई क्या है. फाई इज द एंगल इन एक्स वाई प्लेन, ठीक है, यानी कोई ऑब्जर्वेशन पॉइंट है ये वाला, so this is theta, और इसका प्रोजेक्शन ले इस प्लेन में, so this is phi. So ये x है, तो x y प्लेन में प्रोजेक्शन का जो एंगल है x एक्सिस के साथ वो phi है, और z एक्सिस के साथ एंगल जो है वो थीटा है. तो लेट्स से अगर आप xz प्लेन में पैटर्न देखना चाहते हैं कि रेडिएशन कैसे स्प्रेड है वर्सेस थीटा, तो xz प्लेन में phi जो है वो 0 होता है. So when phi is 0, this is 1, so we have 1 minus sine square theta, which is cosine square theta. So this is cosine theta in xz plane. So इसका मतलब है यहाँ पे 1 है, और फिर जब theta 90 होगा 0 होगा, and then when it goes there it's 1 again, right? So it has a pattern which is maximum here and then minimum, provided that, okay, when theta is 90, whatever this is going to be 0. So when theta is 0, so this is 0. So we have 1. When theta is 90, it then depends on phi, because when theta is 90, this is 1, but in xz plane this is 1, but since phi is also changing, this is also changing. So you can see this total behavior You see anything?
Windows
P और P अच्छा इसको पहले select करते हैं। Okay, so you see that this is the function that we have to plot, right? 1 minus this bt is beta, cosine this th is theta. अब वो ठीक है, मैं उसको बड़ा कर दूँ। तो मैंने जो प्लॉट किया ना इस सारे फंक्शन को प्लॉट, ठीक है? तो ये 1 माइनस बीटा कोसाइन थीटा उसके अंदर ले रहा, तो ये 1 ओवर ये 3 हो जाएगा और ये 1 ओवर यहाँ पे 5 होगा। Increase the font, okay? Can you see now? थोड़ा और बड़ा करो। So this is the function. This is 1 minus beta cosine theta cube minus sine theta into cosine phi square divided by this gm is gamma square into 1 minus beta cosine theta whole power phi, where beta is variable on top and gamma is 1 over square root 1 minus beta square. And I'm plotting theta from 0 to pi and phi from 0 to, let me make it 2 pi initially. So let's begin with beta roughly 0. You can actually work from 0 here as well. So let's see. It's this. Can you see it? वो मैं आपको बता दूँ कौन सा। So the particle is right at the center of this donut, and it's going up, okay? And the point that is in the center of this donut is the origin. So on the top is roughly z-axis, the x-axis is roughly here, and to the right is the y-axis. So now you can imagine like this. So it's something like this. Particle neutron. So I'm यहाँ पे origin पे, and this donut is right here. So emission along y-axis is 0, roughly speaking, and its maximum in this way. So जो particle है, it's tangential, it's roughly towards up. आपको उसकी थोड़ा सा अंदाजा हो जाएगा कि कहाँ पे है, when I increase the beta. नहीं rotate हो सकता है मतलब थोड़ा सा rotate that's why it seems like there's only a small point where it is 0, and that makes sense, right? Because there's only one point where this function is 0, and that is when theta is 90 and phi is 0. Because only then this is 1, at all other points it's smaller than 1, and then this is greater than 0. So theta 0 is the z-axis, and theta 90 is the y-axis, in the xy plane, phi 90, and phi 0 is the x-axis. So it's only one direction along which it is zero. Otherwise, it's other than that. So the interesting situation is that when this beta increases from zero, this is a little bit modified, but still almost the same. एक चीज आप देखें कि beta 0 और beta 0.1, which is 10% of velocity of light, there's not really much difference. So when we take low speed limit of these formulas, they're actually valid for a huge range of speeds. So even for 0.2,
beta 0 की तरह से नहीं आ रहा.
beta 0 it was symmetry. But now as you see the beta is increasing, in the direction of the speed, the balloon is getting a little bit bigger. Let me make it quick. 6. So the balloon is still a bit wider, though evidently अब जो radiation है वो ज़्यादातर front direction में, लेकिन अभी भी फैली हुई है काफी. As it becomes, let's say 0.8. So then it's almost like a pencil beam. 0.9. So the particle is right here at the bottom.
0.999.
Out of the mathematical range, so we make it
एक नहीं है, दो नहीं.
double the interquarter.
Double नहीं.
So this is pretty short. So this is about 0.9. So now you get the idea. और अगर particle जो है lights on, if it is moving slowly, so यूं जा रहा है तो ये इस डायरेक्शन में ज़्यादा रेडिएट कर रहा है. अभी यहाँ पे है तो इस डायरेक्शन में ज़्यादा इधर रेडिएट कर रहा है. चलता चलता अगर यूं आगे सर्कल में इमेजिन करें, so it's radiating like this. So when it is moving very fast, then it's radiating right in its own direction. मैथमेटिकल इसलिए बहुत अच्छा और आसान सॉफ्टवेयर है. आप लोग स्पेशली चीज़ें विजुअलाइज करना चाहते हैं तो इसको इस्तेमाल करें.
Yes, sir.
रिप्लेस किया ये भी पर क्या भी जब प्रोटेक्टिव.
Anyway, okay, so let's now get back here. आपने देखा है कि ये फंक्शन जो है ये जब हम अल्फा relativistic region में है, so all the radiation is for small theta. So that's why I approximated this using this additional approximation of small theta. Now you can actually see from this function as well that you can find the beam width. क्योंकि अगर इसमें देखें, when theta is small, so this is यहाँ पे कोसाइन स्क्वायर थीटा है, इसको भी मैं फिर थीटा स्क्वायर लिख देता हूं, so this becomes theta square. अब जरा देखिए, when theta is 0, right along the z axis on the top direction, so this is 0, so this is 0, so this is 0, so this is 1 because theta is 0. So this part of this function is 1. Now when theta is 1 over gamma, okay, so when theta is 1 over gamma, this is what?
4.
So this is 4, and with this thing, and this is ये से कैंसिल हो जाएगा, so this is 1 plus beta square, which is 1 over gamma square. हाँ ठीक है, क्योंकि वो नहीं आ सकता. This is 1 plus beta square whole square, and beta is roughly 1. So this is 1 plus 1, 2. 2 square is 4, so 4 goes with 4. So essentially we have 1 minus cosine square phi. And let's say at phi is equal to, so this thing is now order of 1. This varies between 0 and 1 because phi can go through. So this function is roughly 0 at phi is equal to at least 0. So all of the radiation is confined between theta 0 and theta roughly 1 over gamma. So the beam width is of the order of 1 over gamma. So larger the gamma is, the smaller the beam is. Or actually, this is one of the ways of producing synchrotron radiations, high energy synchrotron radiation. There are few synchrotrons in the world, और उनमें जो रेडिएशन प्रोड्यूस की जाती हैं, उनका एक तरीका ये भी होता है that you first have a linear accelerator which accelerates the charged particle linearly, and radiation from these particles are small, and then you have bending magnets here. Simply, let's say is a magnetic, strong magnetic field provided perpendicular to this. The particle turns like this, and at this point there is a sharp radiation beam in this direction, and you have your experimental setup here and the sample that you want to irradiate or whatever you want to do with this sharpness. And you can either reuse the scheme or you can simply absorb it at some positively charged terminal if these are electrons. Usually electrons can be easily accelerated to relativistic velocities in a linear accelerator as well, because they have very small mass. A small push can accelerate them very well. So these electron lasers, laser is something else, but these electron radiation sources are used in this way. So इस तरह से जब इनको use करते हैं, this is called synchrotron radiation source. There's another way of producing high energy beams from these electrons. So instead of having these strong bending magnets, people can have this arrangement as well. So you have a linear accelerator, so you're accelerating the electrons. So इस region में आके you have these magnets which are called undulators or wigglers, north, south, north. So इसमें क्या ये बल्कि actually they are perpendicular to this plane. They are not in this plane, they are in this plane. So magnetic field is this way. So there is a magnetic field, let's say out of the board, this is into the board, then there is a magnetic field like this, then magnetic field like this and that. So U electron आ रहे हैं, जब ये यहाँ पे आएंगे, so they will feel a force, let's say in this direction, they will go a little bit. Then there is a magnetic field in the opposite direction, they will feel a force in this direction. And then there is a magnetic field like this, so they keep going like this. So इसमें क्या होगा? Wherever they are here, they are feeling a force like this, which is an acceleration perpendicular to the direction of motion. So यहाँ पे क्या है? Acceleration perpendicular. Everywhere the acceleration is perpendicular to the motion. तो यहाँ पे आके आप इनको सीधा कर देंगे. तो
रेडिएशन पास कर देंगे.
हाँ, और acceleration बेशक इस structure में हो या structure में हो, because we have beta dot square. Only the polarization changes, but the radiation intensity direction remains the same. So you have a strong beam of radiation in this direction with this bigger thing. So there's a free electron laser which is made with a similar concept, because in an electron laser, जिसको हम देखेंगे detail में, you have to reinforce radiation. So this is just incoherent radiations, because all electrons in different points, they're radiating independently. But if you can bunch electrons together, there's a group of electrons here, and when it is radiating, depending on the frequency of the radiation which you want to maximize, you have electrons radiating in a later point with the same phase, so that all radiations add up coherently. Then we can have a free electron laser, which is based on bunching electron groups together in different parts. But in all of these situations, the source of radiation is this acceleration perpendicular to the direction of motion. So you get a beam in the direction of motion because of this perpendicular acceleration. Any questions? Okay, so we will get back to this free electron laser after we developed a way of characterizing the frequency distribution of these radiations. अब तक हमने जो बात की है, we didn't say anything what is the spectrum of these radiations. हमने intensity की बात की है और angular distribution की बात की है. But of course, electromagnetic waves can be expressed as a spectrum of different waves with different frequencies, right? And that's what usually we do. So let's now try to do a spectrum analysis of these waves. You can have a brute force method. आप किसी भी radiation pattern का फर्ज करें, ये radiation pattern है, आप ये find करना चाहते हैं what's the frequency quantum. All you need to do is take a Fourier transform, right? Because this is a function of time. अब t prime में है, अगर आप t prime में जो charge particle का frame है, उसमें radiation spectrum देखना चाहते हैं, तो you can take a Fourier transform from t prime to frequency. Simply multiply with the exponential of omega t, integrate over t. You have a Fourier spectrum. If अगर आप observer frame में करना चाहते हैं, you convert it into with respect to t, उसमें Fourier transform ले. So with the Fourier transform, and अभी तक यहाँ पे जो हमने general motion रखी हुई है, so it's general. Depending on the profile of beta dot, you will end up with the various spectrums.
Exact expression है हमारे पास frequency का.
It depends on the motion of the particle.
Power expression है तो frequency के लिए expression नहीं डाल देते.
We can find an expression. फिर देखिए फर्ज करें, आपको मैं कहता हूँ beta dot is 2t. That's so the acceleration is this. Yeah, I can give you a constant acceleration. Suppose at any function. So you now have beta dot, and then you can find beta because of the acceleration. Velocity is a time dependent quantity, right? And then you have this function of time. So depending on that function, you can take the integral and find the Fourier transform. Okay. So I'm going to do in a few cases. और Fourier transform से I will do it, but bit later. Let me first do a simple problem in Fourier domain, and that is of a circularly moving charge. So we have a charge particle which is going in a circle of, let's say, radius r with frequency omega naught. So what I'm interested in is finding its spectrum at this point due to this circulating charge.
ये XY plane में
Let's take it to be an xy plane. Okay. Let's take it to x. And this is y. अब देखिए, अगर तो आप इसका टाइम डिपेंडेंट स्पेक्ट्रम चाहते हैं तो we already have the distribution formula there, right? आप उसको देखें dp over d omega, which is for perpendicular acceleration. अगर उसको आप इंटीग्रेट कर दें कहाँ से? Let's say you integrate it over one time period, then you can have the average or total field after time integration, but we can find, let's say, the total radiated power as a function of time by integrating that distribution over the solid angle. ठीक है? For circular motion. क्योंकि वो जो रिजल्ट है वो जनरल है, ठीक है? लेकिन अगर आप उसी को सर्कुलर मोशन पे स्पेशलाइज कर लें, you can find the total power. But here I am interested more in the Fourier spectrum, the frequency contents of these radiations. Or by the way, I have the total power. Let's see. Yes, and let's do that. If you want to find this total power, so this is simply 1 over 4 pi epsilon naught e square beta dot square 4 pi c 0 to pi sin theta d theta 0 to 2 pi d phi 1 over 1 minus beta cosine theta cube minus sine square theta cosine square phi gamma square right? So this is the total radiated power over all angles over theta and phi. अगर आप वहां से हम टोटल पावर फाइंड करना चाहते हैं एज अ फंक्शन ऑफ टाइम, और ये इंटीग्रल जो है अगर इस टर्म को आप देखें तो ये सिर्फ थीटा का फंक्शन है, तो इसका फाई का इंटीग्रल लेंगे तो 2 पाई आ जाएगा। इस टर्म को देखें तो फाई का जो इंटीग्रल है वो सिर्फ कोसाइन स्क्वायर फाई पे होगा, व्हिच इज सिंपल इंटीग्रल। आई एम नॉट गोइंग टू डू द इंटीग्रेशन, आप इसको कर सकते हैं आराम से। और जो थीटा इंटीग्रेशन है इसकी वो है साइन स्क्वायर थीटा over 1 minus beta cosine theta। अब अगर इसको आप देखें तो इसकी इंटीग्रेशन आराम से की जा सकती है। ये sin theta है, sin theta d theta over cosine theta, so let's say I take cosine theta to be x, so then sin theta d theta would be dx, so it's simple dx over 1 minus beta x cube। और इसमें इंटीग्रेशन होगी sin square theta which is 1 minus x square, अगर cosine theta को मैं x लेता हूँ तो 1 minus beta x, और 1 minus x square जो 1 over ये टर्म है वो फिर उसी तरह की इंटीग्रेशन है जो x square over 1 minus beta x वाली इंटीग्रेशन है उसको आप बाई पार्ट्स कर लें और ये आराम से इंटीग्रेशन होगी। एंड द आंसर इज 1 over 4 pi epsilon naught v dot square 3c cube gamma 4। total radiated power over all angles. अब अगर आप सर्कुलर मोशन का स्पेक्ट्रम फाइंड करना चाहते हैं, you can actually do it from here as well. You have to find its Fourier transform, and you can do that. और v dot by the way ये सर्कुलर मोशन में होता है, एक्सेलरेशन होता है v square over rho. So you can put v square over rho here, and you will have a function in terms of velocity and radius.
Velocity भी दोनों की यार, velocity का मॉड बताइए, circular motion है.
So velocity will be basically r rho omega naught, right? So then rho square ये हो जाएगा rho omega naught. So in terms of omega naught, you can put this v dot like this. So you can write it in various ways. अब by the way इसमें जरा देखिए, अगर मैं ये v dot करूँ तो this will be a rho dependent function, radius dependent, and radius is dependent on the inertia of the particle. अगर हम charged particle को magnetic field में देखें, so before I do it, let me just analyze this circular motion. So if we have, let's say, this charged particle in a circle because of some magnetic field, so then we can find its angular frequency by equating the centripetal acceleration with the magnetic force. This is if the B is perpendicular to velocity, so this is EV, B is the magnetic force. And since this is, I'm taking relativistic case, so m gamma is the mass, and v square over rho is mass, velocity square, and this thing. So यहाँ से you can solve it either for v. So v would be EV rho over m gamma, or if you want to solve it in terms of omega naught, then omega naught is EV over m naught, because v is rho. So this is the angular frequency of this charged particle in a circular motion due to a magnetic field. So यहाँ से ये वैसे देखें, अगर आप initially एक charged particle को circular motion में डाल देते हैं, suppose you have some source of particles which are coming in, let's say they are coming with a constant velocity v, you have in this region magnetic field, and they begin to go in a circle. Will they remain in a circle?
उसी से रिलेटेड हाँ नहीं क्योंकि radiation emit कर रहे हैं तो use कर रहे हैं
Well, they have to emit radiation, and because they are emitting radiation, their energy is decreasing, so their radius is decreasing, because their kinetic energy is proportional to the velocity, and since velocity is decreasing, the radius would have to decrease because of this equation. So that's actually, this was a thing which was known to people before people came to knew of the electrons and protons in matter, and that was one of the biggest objection to Bohr's model, that if the electrons are circulating, then the atom cannot be a stable particle, because eventually they will radiate all their energy and they will die from, because the electron would collapse on the proton. So this is the frequency, the angular frequency of motion of a charged particle in a circular motion. So you can find it from here. But right now I am not concerned with this problem. What we are concerned with is that we have a charged particle in circular motion in XY plane. Let's say here, so this is the particle going. So this is some angle phi, which is omega naught t prime, because this is increasing. Then we want to find the field at some point P as a function of frequency. I want to find the weight of different frequencies that are radiated. So one thing we can see immediately. This is a charge and current distribution which has a frequency omega naught, a fundamental frequency omega naught. Right? So it means that other frequencies would be a multiple of this omega naught. So even if you forget about everything, you just concentrate on this thought. This is a charged particle which is undergoing a periodic motion. So we know from Fourier analysis that if there is something periodic which have some frequency omega naught, these quantities are fields which are associated with this thing, they will have that fundamental frequencies and the multiples of that fundamental frequency as well. So in general, our field will have a frequency omega naught, then 2 omega naught, 3 omega naught, 4 omega naught, and so on. So it means that the fields at this point can be written as, so a general R and T dependent field can be written as a Fourier series in the like this, where there is a Fourier coefficients L, T. So we can do it from the field as well. But since fields come from the potentials, it's easier to do it from the potentials. And since potential have simpler form, we can do it from the potential. And our interest is only at a point where R is larger than this thing. Okay, so this is RP. RP is cosine omega naught T prime x hat sine omega naught T prime y hat. So this is the position of the particle in xy plane. So by assuming, and let me say its radius is rho, that the observation point R is much far away from this circular motion, it would be easier to solve this problem using potential, because when we are far away, the expression of fields from potential is also much simpler than the one that I have written.
So we cannot L here.
N is this index. We have Fourier series of this, we have a form like this, which is essentially saying that we have one frequency omega naught, then L for L2 we have omega naught 2 and so on. Okay, so instead of doing it from the fields, let's do it from the potentials, which is much easier. And I wrote the potentials here. So this is the vector potential. So let's begin from here. And for this I need not only RP, I also need V. So V is RP dot. इसका लेंगे डॉट तो ये आ जाएगा माइनस ओमेगा नॉट मैंने बाहर ले लिया. So this is the velocity. Now we substitute this P and RP into, let's say we do everything in T prime. So mu naught E 4 pi 4 pi mu naught E 4 pi kappa. So kappa is 1 minus n dot beta PHY. This is V kappa R minus R, and f of t prime is equal to 0. So this is our A function, and I want to express it in terms of a Fourier series. And before we do that, let me just simplify it. So this V is given here. So this V is here. It's too big to write here again. So the kappa is 1 minus n dot beta, and this R minus R. Now let me do this approximation in the far field. So because we are going to need it. In far field, we can approximate this quantity like this. You see, let me draw it here. So this is the charged particle, and this is RP. So this is R. And let's say this is the origin. This is R, and this is R minus R. If this R is very large, then this thing is approximately equal to R. R is from here to here minus this part. And what is this part? This part is the dot product of this unit vector with this thing. Right? When R is large, this is this length minus this part.
So ये rho क्या होगा?
Rho is the radius
हाँ?
of the circle.
फिर कौन? क्या ये इलेक्ट्रॉन स्क्वायर है शायद?
कोई भी हो charge particle. So its radius is rho. That's why RP is rho cos and rho sin. So जो ये वाला फैक्टर है, ये इससे अप्रोक्सीमेट में देते हैं। जो 1 माइनस n डॉट बीटा है, उसके लिए हम n जो है पहले उसको लिख लेते हैं। n in spherical coordinate is sin theta cosine phi plus sin theta sin phi plus cosine theta z है। ये है इन जनरल n। अच्छा, इस प्रॉब्लम में एक चीज देखिए, ये देखिए यहाँ पे चार्ज पार्टिकल सर्कल में मूव कर रहा है, तो यहाँ पे जो पोटेंशियल है या फील्ड है वो वही होना चाहिए जो यहाँ पे है, जो यहाँ पे है, तो यहाँ पे। इट शुड बी इंडिपेंडेंट ऑफ फाई, क्योंकि प्रॉब्लम जो है इट्स इंडिपेंडेंट ऑफ फाई। ठीक है, तो अब बजाय इसके कि फील्ड किसी जनरल n पे फाइंड कर दें, आप किसी भी स्पेसिफिक फाई पे फाइंड कर लें, it would be the same at any other phi, but it will make our life easy. So let's say we do it at phi is equal to 0. So when phi is 0, this n is sin theta, x hat, this is 0, plus cosine theta z. और normally radiation problem में this is a standard trick. Any problem that has azimuthal symmetry, people usually only work out at phi equal to 0. Now we have this n and beta, we have to evaluate beta as well. And beta is nothing but V over C. Now n dot beta can be easily evaluated. N dot beta is So this is n, and that is v. So rho omega naught over c, rho omega naught over c, और x का x के साथ डॉट होगा, and we get sin theta, sin omega naught t prime with a minus sign, and x dot x is 1. जो y है उसका दोनों के साथ 0 हो जाएगा. So that is all we have. N dot theta is minus rho omega naught c sin theta naught. Okay, so which means that A can be approximated. Okay. If I have to find the frequency component, you can express this as AL of R, exponential minus 0.1 of NT. Let's do it into D prime, and then these ALs are 1 over T, 0 to T, exponentially of omega naught. Now, all we have to do is find this integral, and we will know the weights of different frequency components. So this integral AL 1 over T, और ये जो AL की वैल्यू, A की वैल्यू यहाँ पे आ जाएगी, इसमें म्यू नॉट E कॉमन है, 4 पाई भी बाहर आ गया, और इंटेग्रल के अंदर सिर्फ रह जाएगा V की जगह पे आ जाएगा rho omega naught minus sin omega naught t prime x hat plus cosine omega naught y hat, और एक एक्सपेंशन फैक्टर भी अब आ गया माइनस आयोटा ओमेगा नॉट एल टी प्राइम. और लेकिन टी प्राइम की जगह पे क्या आ जाएगा? टी प्राइम वुड बी minus iota omega naught L. This is T minus R minus R T over C. और नीचे आ जाएगा कॉपर. Let me see if we are okay. Okay, so actually I'm working in DT. We can work in either, but let's say we are in DT, then this is this, and in place of T prime, we have this thing, and this is copper over R minus R. So, if we are in dt and this is in t prime, we can convert this part into t by eliminating this kappa. ठीक है? ये है t prime. So we are working in the t domain. Then Actually, we can choose to work in either one. So suppose that we are working in T, that we are working in the observation frame. So let's say everything, this is T, and this has to be converted to T, and then this is T. So this is T, then yeah. So this is, let me just first write it. So this is T, this is dt, and this is kappa. So if we are in T prime frame, then we can either convert to T prime or we can remain in T. If we are in T, then this function remains as it is, and then we have to evaluate kappa in T, but it would be much easier if we can convert all of this into T prime, and then we can convert this part into T prime as well. Because this dt can be written as dt by dt prime, and this is nothing but kappa, and so we can replace this dt by kappa dt prime. So integration will go to so this rho omega naught, let me just take it out. So this is rho omega naught out. So ये dt की जगह पे I'm putting dt prime. ये kappa इस kappa से cancel हो जाएगा, and this exponential factor is minus a omega naught L T prime minus R minus RP over C dt prime, और यहाँ पे आ जाएगा. अब ये जो चीज है माइनस साइन टी साइन एक्स स्क्वायर कोसाइन ओमेगा टी प्राइम वाई जेड आर माइनस. चलिए अब हम उसको देखें. ये जो चीज है, we have actually already seen that we can approximate this thing like this, r minus n dot rp, or ये n dot rp भी we can work it out, right? So this is n and this is rp. So let me just forget this constant factor. This is some C2. अब जो है अभी यहाँ पे देखो, ये R minus RB की जगह पे I can put R minus something, वो माइनस बाद में लिखते हैं, लेकिन जो R वाला पार्ट है ये हो जाएगा माइनस इंटू माइनस आयोटा ओमेगा नॉट L R over C, and I can take it out of the integral and write it simply iota KL R. और KL जो है an application for omega naught L over C. ये समझ आ गई. ये जो एक टर्म है R वाली वो मैं बाहर दे दूँ क्योंकि वो ऑर्डर करना है. अब दूसरा ये जो है ये भी है R minus NP dot R. ठीक. So R minus this part. लेकिन जो एक्सपोनेंशियल फैक्टर है उसमें ये पार्ट इंपॉर्टेंट है, और नीचे जो है इंटीग्रेशन को सिंप्लीफाई करने के लिए सारे को मैं जस्ट R लिख सकता हूं. ओके. X है, Y है, और यहां बाकी बनेगा माइनस ओमेगा नॉट T प्राइम और जो NP डॉट R है वो ऑपरेटिव कॉलिंग का बनता है रो ओवर सी आ जाएगा इनको, और यहाँ पे क्या आएगा, और x का हमें x के साथ तो साइन थीटा कोसाइन ओमेगा नॉट टी प्राइम आ गया, साइन थीटा कोसाइन ओमेगा नॉट टी, ये आ गया। यहाँ कहीं L भी था, ये देखिए जो अप्रोक्सीमेशन है वो हमने एक्सपोनेंशियल और यहाँ पे डिफरेंट रिस्पॉन्स, यहाँ पे मैंने सारे को जस्ट आर ही लिख दिया, लेकिन यहाँ की जो स्मॉल पार्ट है आई डिड इग्नोर इट। उसकी वजह ये है कि जो एक्सपोनेंशियल फंक्शन है इट्स अ वेरी सेंसिटिव फंक्शन ऑफ स्मॉल चेंजेस, क्योंकि ये क्या है, ये कोसाइन और साइन। तो आप फर्ज कर लें कि जो r है इट इज 1 किलोमीटर और जो n डॉट rp है लेट्स से दिस इज 0.1 सेंटीमीटर, ठीक है। नीचे जो है वो 1 किलोमीटर प्लस 0.1 सेंटीमीटर इज ऑलमोस्ट 1 किलोमीटर, क्योंकि उससे डिवाइड भी कर लें। अब 1 किलोमीटर से डिवाइड कर लेंगे या 1.001 से डिवाइड कर लेंगे, आंसर इज ऑलमोस्ट द सेम। यहाँ पर क्या है, क्योंकि आपने कोसाइन लेना है और साइन लेना है, तो कोसाइन साइन में जो एब्सोल्यूट वैल्यू है वो इंपॉर्टेंट नहीं होती, क्योंकि इट्स अ मॉड फंक्शन ऑफ 2 पाई बाई 2। तो 2 पाई का कॉस और 2 पाई इनटू 1 मिलियन सेम आंसर, लेकिन 2 पाई इनटू m समथिंग प्लस, even if this is small with compared to this one, this number critically depends on this thing. So phase के अंदर जो है even a small part has to be kept. और यहाँ पे हम इंटीग्रेशन सिंप्लीफाई करने के लिए इसको इग्नोर कर सकते हैं, doesn't matter. So हमारा इंटीग्रल जो है वो ये बन गया है, which unfortunately cannot be solved using elementary functions. It is in form of Bessel functions. So that's all that we can get to. And after that, this actually just an identity. This sine omega not t prime into this thing is a Bessel function of order L, and this term into this thing is a Bessel function, the derivative of a Bessel function of order L, and we can write the answer directly. लेकिन जो इम्पोर्टेंट चीज़ है जो हम नेक्स्ट सेक्शन में करेंगे वो है इनकी relative magnitudes, और we will actually discuss that in the next class. So before you leave, just to give you a summary, क्योंकि उसका होमवर्क में मैं इस तरह का एक प्रॉब्लम दूँ, आप जो स्पेक्ट्रम है in general you can always use what I will call the brute force method when you have the time dependent power distribution, either total or angular distribution. आपने अगर frequency quantities find करने हैं, you can immediately take the inverse Fourier transform and find the frequency spectrum. Okay. यहाँ पे मैं इसलिए इस तरह से कर रहा हूँ, I want to get some physical picture in simplified manner. So जो circular motion है उसका हम spectrum जो है वो find करने की कोशिश कर रहे हैं। तो क्योंकि ये सर repetitive motion है, it means that the potential functions and fields they can all be expressed as Fourier series, और ये जो different weights हैं in Fourier series के they will actually tell us the relative magnitudes of different frequency components in the radiated spectrum. और astronomy में actually they are very critical. Okay, if there are charged particles which are emitting in a faraway star, you can tell the nature of the star by observing the frequency spectrum. आपको पता चल जाएगा कि if there are charges that are going in circular motion, or maybe they are going in some linear acceleration, and also from circular motion you can know the value of the magnetic field present in that star. So we can do observation and prediction based on the spectrum of the waves that we get from those particles trapped in those faraway stars. So actually I'll continue from here in the next lecture.
तो क्या